Last week, we saw a general overview of all the elements of TCP-IP. What remains to see today is a few words about the physical layer. Physical layer is not the topic, the focus of this course. It is the focus of courses such as communication theory, but we will need to say a few words for as far as it impacts what we're doing. The physical layer translates bits or blocks of a few bits into waves that are practically always electromagnetic waves. And the first element of the physical layer that's of interest to us is whenever there is a physical channel between two devices, we're interested into the bit rate, which is the number of bits transmitted per time units. That's in kilobits per second, gigabits per second, etc. In the context of computer networking, the computer networking guys very often call this bandwidth. But if you go to the communication theory course and you call it bandwidth, probably the teacher will not like it. The bandwidth is in hertz. It's a physical thing. It's the width of the spectrum that we use for a given channel. And the bits per second is the correct name, or the bit rate versus the bit per second. But invariably, if you read SIGCOMM paper or any documentation from Cisco, you will see bandwidth as a synonym for bit rate. Here is the link between the two. In fact, as you know, that is the goal of information theory, to say what is the usable capacity of a given channel. A channel is defined by its bandwidth, but also other properties. What happens, what are the kinds of impediments that can occur on the channel? The simplest model of a channel is a channel where there's only white noise. Then if there is only white noise on the channel, we have this formula that links the signal to noise ratio, which has to do with how much power you're sending into the communication link, to the bit rate, to the capacity here, and B is the bandwidth. And the capacity is, from information theory, is the upper bound on the available bit rate that any system can implement. And in practice, there exists for most systems, for most channel models, there exists practically implementable coding schemes that are extremely close to the capacity. So in practice, we can really approximate the capacity with the available bit rate here. So bit rate is one thing. We've seen already last week a first reference to another thing that plays a role for us. It's propagation. Here I'm showing on a time and space diagram where time is flowing horizontally and space is on the vertical dimension. A is sending some information to B. What happens if we put an oscilloscope on the line? We will see the electromagnetic waveform. Here I'm showing a square waveform, which is, I'm trying to show it, but somebody's hiding it. Thank you. Which is very primitive coding schemes on very simple channels, use that type of signaling. And of course, when it goes through the channel, it will not be a nice square waveform received at the other end. But for simplicity of this diagram, I'm showing this here. But what we show here is that the time it takes for the signal to propagate is non-zero. That's exactly the propagation time that is shown here. So the propagation time is really the time for the front of the wave that carries the bits that you're sending to reach the other end. So we see the propagation time as the difference, S0 minus T0. And then the bit rate gives how much time it takes to send a number of bits into this channel. If the waveforms that I'm showing here are taking 1 nanosecond for each of those, and if a wave signal carries 1 bit, then we'll have 1 gigabit per second, and we can compute the time it takes to transmit something as a function of the bit rate. So it's important to be aware that there are those two things, bit rate versus propagation speed. The bit rate is changing all the time and is improving so far, almost following Moore's law. So we have a constant increase of the bit rates. 20 years ago, Ethernet was at 100 megabits per second. Now, if you have an Ethernet at 100 megabits per second, probably you're already using obsolete technology, or you want to use Ethernet over a very long distance, which is not typical. So the minimum local area network speed is 1 gigabit per second today. So that increases all the time. But the propagation doesn't change. The only thing you can change is whether you are using cables or free space. In cable, you have a speed of light which is 2/3 approximately of the speed of light in free space. So if you use satellite links at low orbit, then you might have smaller propagation time than if you use cables that are used because of this phenomenon. If you use satellites that are at high altitudes, then the distance to the satellite will make the propagation time very large. If we count how much time it takes for the speed of light for the light to propagate around the Earth in optical fiber, which is the technology that is dominant today for communication with Australia, for example. In the coming decades, we might have low orbit satellites that would slightly improve this. But today we have 200 milliseconds. So 200 milliseconds is negligible if we talk in this room. Is not, in fact, is not negligible for speaking. We consider that speaking is the same as if we were in this room if the latency is precisely around 200 milliseconds at most. 150 milliseconds says the ITU standard. So when we go beyond these, we start having the effect of latency, which is what we see when we use Zoom or other video conferencing software to talk to people that are very far away. Then this latency is visible. And if you talk to somebody in New Zealand or Australia, there's nothing you can do. You will have this latency, even if you improve everything in the internet. For example, those are the times it takes to send one packet of 1K bytes, so 8,000 bits, relatively standard IP packet. Depending on the type of things you are, if you're in a data center, we're talking of 0.1 microsecond for propagation and a minuscule fraction of this for transmission. But if you are talking over the internet, then probably the times are reversed. So this is a pessimistic view of the internet where I have 1 megabit per second end-to-end, which is perhaps what I get when I download transfer from a busy server at the other end of the world, but I might get more with newer generations of networks. So we see that depending on where we are, the time it takes to send a packet may be dominated by propagation or transmission. Let's see a very simple protocol. That's our first example of a protocol. We will study a more sophisticated protocol called TCP, which this protocol is the stop-and-go protocol. The stop-and-go protocol is a protocol we use when we send one block of information and we want an acknowledgement, because as we will have discussed last week, and as we will discover again and again, in the internet, we can never be sure whether a packet reaches the destination other than by receiving an acknowledgement or some form of confirmation here. So the simplest of all protocols is called the stop and go. It consists in sending a packet, waiting for an acknowledgement. So the protocol dictates that whenever you receive a packet, you send an acknowledgement. And if everything goes well, you receive acknowledgement, and then you continue. If the packet is lost, like packet 2 here, no acknowledgement will come back, and then you will detect that there is a loss by timeout. So you wait for some time, which is at most T1 here, which should be larger than the time it takes to send the packet and get the acknowledgement in the normal case. So if T1 is large enough, then we're pretty sure the packet or the acknowledgement has been lost. In fact, there's no way to differentiate between the two. And then we retransmit, we send it again. This is the simplest of all protocols. That's a protocol that is used, for example, when you have very primitive things. When you bootstrap communication, that's what you do when you initialize, for example, a cellular link over between your smartphone and the radio access network of Swisscom or Sunrise. And this is also what is done very often when we communicate in a machine over the bus between two blocks of hardware in a machine. Let's analyze the performance of the stop-and-go protocol in the very good case where we don't lose anything. If we lose something, we will talk about it a bit later. If the packets are not lost, then what is the performance of this protocol? Well, I want to stress here the influence of two factors. One is the transmission time, which is dictated by the bit rate. The time it takes to send one packet is the length of the packet divided by the bit rate in bits per second. And then there's the propagation time. In fact, two ways. I send the packet, and then I wait for the acknowledgement. Plus, there's also the time to receive correctly the acknowledgement. So we have useful time, which is the time to transmit. If I have a channel at 1 gigabit per second, the red part here is my useful use of the channel here. Then I have overhead. This is time that is wasted. The overhead is 2 times the propagation time, assuming it's symmetric here. So that's the round-trip propagation time, plus the time to receive an acknowledgement here, which is also overhead. And then what we can call the throughput of the protocol. Throughput is measured in bits per second, same way as bit rate. Throughput, the difference between bit rate and throughput is the useful part of the bit rate. Throughput is the number of bits you send per second, of useful bits sent per second. Now, in this very simple case, I assume the source is greedy, so it's sending things. There is no loss, no packet, no acknowledgement is lost. We see that the system becomes cyclic, and there are cycles. Here is one. Over one cycle, the useful part is L over B, and all the rest is overhead. So the throughput is a fraction equal to this divided by that, which gives this formula here, multiplied by the bit rate. So the fraction of the bit rate that is used is the red over the total cycle. So that gives this simple formula. In this formula, we see something that appears that has a significant, some significance for us. This term, we see that it's the bit rate divided by 1 plus L prime over L. This is the number of bits that are overhead in some sense, L prime. So that's, we lose some bandwidth because we are receiving bits that are not the data we're sending. Plus another element here, which is 2 dB. D is the round-trip propagation time, and B is the bit rate. So that's the product of the round-trip propagation time and the bit rate. Physically, what does it mean? Physically, it means that's the number of bits that are in the wires, that are on the fly. So that if I send at 1 gigabit per second and the round-trip propagation time is 1 second, then there are 1 gigabits, 10 to the power 9 bits that are being transmitted somewhere or returning, but they're in the wires. They're not received, they're not sent anywhere. This is called the bandwidth delay product, because computer scientists call B the bandwidth, and that's multiplied by the delay. And that quantifies, in some sense, the type of networking situation we're in. Here I showed a very local, high bit rate, but very local, or here, perhaps high or medium bit rate, but very remote. And we see that the bandwidth delay product in those two cases are the same. So in fact, what matters is not very much whether the distance is very large, but it's more the relation between the two given by this bandwidth delay product. And if I look at the performance of the throughput of the stop-and-go protocol, we see that when we are very local, even at very high bit rate, then the throughput is, when the bandwidth delay product is large here, which is either because we are local, but the bit rate is extremely large, or the bit rate is not very large, but the distance is very large, then we see that in both cases, the stop-and-go protocol do not work well. In fact, they are not. The efficiency is 3 to 4%. That means that if you're wasting 96% of the transfer capability when using this. So this is why we need to invent other things. If you are on systems that are low bit rate, for example, if you're controlling the thermostat by sending messages to a thermostat and waiting and making sure they're received reliably, you send one message every 1 minute, for example, then that's the efficiency of stop and go will be good enough. But if you want to transfer data using TCP, we've seen that TCP does the reliability, so we'll ask for acknowledgement. So TCP is a sophisticated version of stop and go. You will need to do something better. And that better will be a sliding window that we will discuss when we talk about TCP. Voila, that's all that we will see of the physical layer per se. And that concludes this first chapter of the course. Before moving to the next chapter, let me do a little announcement. Next Tuesday, it's posted on the Moodle of the course. There is an event for students, so for all of us, organized by RIPE. So what is RIPE? RIPE is the there are two RIPEs. There is the RIPE Networking Center, and there is the RIPE community. So the RIPE community is the community of all people in Europe who are navigating in the world of internet service providers. So all the people who work into the internet, if you want, the people at Swisscom who make the internet available for us, at Switch, which is the internet service provider for Swiss universities, they're all part of the RIPE community. The RIPE NEC is also something else that we will discuss a bit later when we talk DNS. It is the authority that allocates the IP address blocks and the DNS names to Europe. So it's slightly different things. So on the coming Tuesday, there will be a session at 5 o'clock. It's remote by Zoom or similar things with interesting questions like who controls the internet, ethics and sustainability of the internet, and can you run the internet? So I invite all of you who are interested in those topics to join those sessions. You need just to follow the links that are in this page or that are on Moodle. And we will have fun attending this session. Voilà, that's the end of this chapter. Are there questions on this chapter before we move to the next one? Yes, one question? Yes, it's online. It's in person and online. The next chapter in the course is the IP layer. So we don't follow the ordering of the layers. The layers start with physical, culminate in application. So I could start with a physical, then move to MAC, then IP, or start from application, then move to transport, then IP. But I prefer to start in a more random order that is more useful for the labs. That's what we do. So we start with the IP layer. What is the IP layer? Well, as this is showing, the goal of the IP layer is to interconnect the entire world with all the dramas and problems that exist everywhere in the world. The principle, IP is principle. That means it's not a random collection of pieces of software that does whatever you want. No, it's extremely codified and extremely well defined. It's defined by the IETF, Internet Engineering Task Force, that specifies things like the IP and TCP protocol. Of course, once you implement your own software, you could do something that you would call an IP router that would not follow the principles of IP, but probably that would not receive a lot of success because those things are complex, right? The complexity is in the zillions of small detail. So if you don't follow the rules, probably it's because you're an attacker. But in order to understand how the system is organized, we will first see the rules. And IP has, roughly speaking, two principles. The first principle is that the IP addresses are used with longest prefix match. And for that, they are structured here. Every interface has an IP address, and the IP address reflects which network the system belongs to, in the sense of where to send the packets in the network. For example, we've seen that EPFL addresses are 128.178 or 128.179. That's a prefix that identifies EPFL in the world. Every packet contains the IP address of destination. We've seen that last week. That's the principle of the datagram network or the postcard analogy. And every system has, which is either a host or a router. In the principles of IP, we don't really make difference between hosts and routers. Every system should have a forwarding table on which it will perform longest prefix match in order to know what to do with packets. This is illustrated here in this very, very simplified diagram. So in order to make it simpler, I used shortcuts for addresses. With IPv6, addresses are long things like this, so it's a bit complicated to reason about it. But imagine that A is a prefix. A prefix /48 means it's a prefix of length 48. It's a string of 48 bits here. So the routing tables in a router, also in a host, but they're primarily interesting in a router, contain things like a list of destinations and what to do with in order to reach the destination. So there's a number of things, but that are in the table, but the most interesting thing is the outgoing interface, which I call here the output. And a destination is not exactly an IP address, it's a prefix. It's an IP address for IPv6 is 128, so a destination could be a 48-bit prefix. That means the first 4 bits of any potential IP address. And here this router has two prefixes, two entries, A and B. And I put here in the form A star, that means the size, the usable size of the prefix is only in case of A 48 here. What happens when a packet is received by this router? For example, if the packet goes to destination, so an IP address destination, I can mark it in this form, b.d.h2. This is a form that exists only in this slide. When you will see an IP address, you will see all the bits. You will not see the dots between the bits. Right? It's a string of 128-bit. But here, to make the story easier to understand, I mark it as b.d.h2. These dots here, again, are not in the address, but they are in the routing table. For example, at router 2, there's an entry that corresponds to b.d, so we have the /64 here. That says, well, this is 64 bits that correspond to that. What happens when router like A or B has a packet to receive? Well, it goes into the table and looks for a match. Very often, there's only one match, and the thing is easy. That's the case for R1. When it receives a packet to B.D, it tries this matches. This does not match, so there's only one match, then it's easy to do. I will forward it to port number 2. Then the packet destination address is not changed. It's the postcard paradigm of IP, that we don't change the address when we move the packet from one router to the next. We will see cases where we violate this principle, but I prefer first to show the principles, then to show the things we do as violations instead of putting everything at the same level. So when R2 receives this packet, it goes into its routing table. The first line doesn't match. There are 2 lines that matches, line 2 and line 3 here. That corresponds to line 3 says B/48, and line 2 says B.D, which is this one, /64 here. So here there's a match of 64 bits. Here there is a match of 48 bits. And the IP principle says you take the longest match. So the longest match is this one. So we'll send the packet to number 2. And if there is a packet that goes to b.c.h2, then in this router, it does not match this, but matches that one. So we'll go to number 3, and therefore we'll go to router R3. This is the principle of the first principle of IP forwarding. So routers should do this. Why is it interesting? Well, that allows us to aggregate things and have exceptions. For example, here we see that router R2 decides that everything that starts with the prefix B should go to number 3, except for the things that start with B.D. So that allows us to compress the fact that this is perhaps a very large network, and I don't need to have all the subnet prefixes of all this network. I aggregate them in this form, but by aggregating, I'm still allowing that part of the network is another port of this router. So that's really the trick of how the IP layer works. It uses this principle. And longest prefix match simply means we go for the most specific match in the table. The less specific match will never be used if there is a more specific match that occurs. That's the first principle. The second principle of IP is don't use routers inside a LAN, or IP would exactly speaking say inside a subnet. Remember that IP was defined 30 years ago as an inter-networking protocol, as a mechanism to interconnect local area networks. So here I'm showing an Ethernet local area network and a Wi-Fi local area network. They cannot communicate by Wi-Fi or by Ethernet, so we need something in the middle that has both Wi-Fi and Ethernet. And that thing in the middle could be a bridge. We'll talk about that later, but it could be a router. That's the primary way of doing things. And now the second principle, which is fairly obvious but has a number of consequences, says that if B communicates with E, you should not send everything to the router. You should simply find a way to communicate directly. Directly means that we use the local area network technology that allows us to communicate. For example, when B talks to E, they should go via the Wi-Fi base station. When W talks to P, W to P here, they should go through the Ethernet concentrator here. But of course, when W talks to E, they should go via the router, which means they will go via the Ethernet concentrator, the router, and the Wi-Fi base station. So the principle says, inside a LAN, don't use routers, but between LANs, of course, you will need to use routers here. And a corollary of this is that hosts that are in the same local area network, being in the same local area network is a physical layer attribute. I am connected to this Ethernet system, at least to speak of, we'll see that we can virtualize everything, but as a first mental model, it's a physical layer attribute. But that's not sufficient. IP has to know the IP layer information must be consistent with the connectivity that is happening at the local area network. And this is via the subnet prefix and the subnet mask. All hosts in this local area network should have the same subnet mask and the same subnet prefix. The subnet mask is giving the number of bits of the subnet prefix. And for example, if the subnet mask is 24 bits, the first 24 bits of their IP addresses should be the same if they are in the same subnet here. That's the fundamental principle of IP. Things that are in the same subnet, which means are connected to the same MAC layer object, Ethernet concentrator or Wi-Fi base station, this should be reflected in their IP addresses. They should have the same subnet prefix, which is given by the leading bits of their IP addresses, where the number of leading bits is dictated by the subnet mask. Well, let's do a little quiz before continuing. Close and open. Do you see the poll? Yes, I see some answers. Yes?
Yes. So does that mean that like all of the, in the local access network, all of the devices have an IP address? Because I thought last week, and what I understood was like the router with the Wi-Fi station would have like an IP address, and then it would sort of communicate to the correct MAC address afterwards when it received something. But I thought that the IP address was sort of like a public interface that individual devices didn't really have. They just had the router essentially that would like have an IP address off of the rest of the world, and then it would know which MAC address to send it.
Yes, that would be a way to do it, but that's not the way it is done. So the question is, you believed last week that only the router has IP addresses, and those have MAC addresses. And when an IP packet comes to the router, then this one knows that they are delivers them using their MAC address. Could have been the design. It is not the way IP is done. IP says every end system has an IP address, and the only way I have to send data to this end system is to write a datagram with destination address being this IP address. Okay, I close the poll in a few seconds. So the poll is asking, when W sends to P, so you print something and your printer is connected locally to you via an Ethernet concentrator. So you're in the same local area network. Which destination address do we see in the packet sent from W to P? The IP address of P, the IP address of the Ethernet concentrator, one of the interfaces of the concentrator, or there is no IP address because communication is in the same subnet. I close the poll. The majority says A, but a large number of people say C. The correct answer is A. It's the IP address of P. So that's a first principle that we need to remember, that the IP header is always present if we use TCP-IP software, which, apart from very weird, obsolete or quasi-obsolete things, is the rule. Question? There are packets that do not carry an IP header. It's true, we will see a few of them. For example, the R packet uses IPv4. Those are largely old protocols. With IPv6, it's not the case. So yes, in the past, there were non-IP things happening. And in fact, local area networks were using other than IP. Novel Netware for Microsoft Windows environments, AppleTalk for Macintosh environment. They were not using IP addresses at all. So you could do Wireshark and see non-IP packets that have no IP header at all. And there's a few of those that remain in existence in packets today, but they tend to disappear. Normally, no. Normally, if we use IP to communicate, we always have an IP header. And if you think about it, that's a reasonable design to do, because if I take your design, that would say, if I communicate with B, I have to know whether B is in the same subnet as me. If B is in not the same subnet, I send an IP packet that has the IP address of the router, but then I need to know the address of the router. Is that something you really care about? Does the server in California that's downloading content to us needs to know that I am now behind this router and I will move in a few hours and I will be behind another router? Probably not. We're exposing details of the network that perhaps are not useful. Though there are cases where we'll see we do expose them. But the principle is very simple. You need an IP address to communicate, and you send to this IP address. And in fact, the software, when you're writing your application program, you don't care whether you're sending to somebody who is in the same local area network. One word we use for that is online. If W sends to P, and P is online, which means in the same local area network or not, then it should not matter for the software, fortunately, right? If your printer is in the same local area network or not, you hope that you don't need to change something in the configuration of your printing system for that. Of course, you need to give the IP address of the printer or find a way to discover it, but you don't want the software to have to speak to P without using IP addresses when P is in the same LAN, and use it with IP address if it's not in the same LAN. That would be unnecessarily complex and exposing details that perhaps you don't want to expose. Perhaps you don't want the printer to know whether you're on the same LAN or not, if you care about this. Let's talk now about the IP addresses. IP, as we saw last week, exists in two flavors. The old one, IPv4. I say old, but in fact, in practice, is the only one that works always, at least in this part of the world. But it's been obsoleted since 1997. But still, as you see, the inertia of computer networking is huge. IPv4 addresses, as we have discussed, are 32 bits. They are usually, not always, but usually written in dotted decimal notation, because when that was introduced in the 70s, people did not use hexadecimal digits very much. If we would reinvent it today, we would write it in hexadecimal. For example, this is one address, write it in one or the other format. And if you want to look at all the bits, this is the bit string. You might start with the most significant bit on the left here. So we see a block in dotted decimal notation corresponds to 8 bits, and a block of 4 bits corresponds to 1 hexadecimal digit. That's a jugglery we will need to be always doing, so it's better to get used to it. Most of you are familiar with that. So you need to be able to convert, and in order to be able to convert easily, things that are fixed point to remember is that when we have a string of all bits equal to 1, 4 bits equal to 1, that corresponds to the digit F in hexadecimal. the way of writing the hexadecimal digit has evolved over time. Now today we tend to use them to write them in small caps, in lowercase letters. 20 years ago, they were written with uppercase letters, so those things change. And another string that is very commonly found is 8 bits all equal to 1. That corresponds to FF, of course, because it's 2 blocks of 4 bits. And in dotted decimal, it's 255. 255 means 8 bits all equal to 1. Converting from one to the other is, if you're, can be done on paper and pencil, but of course it's easier and less error-prone to use a calculator to do that. For example, if I have this this binary sequence, as you know, the first position here, since we have 8-bit, corresponds to 2 to the power 7. So this is 2 to the power 7 plus 2 to the power 6 plus 2 to the power 3, and so that gives this number. We've seen a highly stylized example of routing table with A, B dot C, etc. Here is how a routing table looks, for example, in the backbone of EPFL. This is a backbone router that makes the interface between the backbone of EPFL and the outside, which is here switch. So ED stands for épine dorsale and switch. So that's the name of the router that faces the two. And here is its routing table. So as you see, it's a fairly simple routing table. In reality, there will be a few other things, but most of the useful part of the routing table is described here. The routing table contains destination prefixes and how to go there, which contains the output port. Here, here I call them south and north, and also for IP, the next hop, which is the IP address of the router to whom I should send the packet to continue. For example, this router here, if we look at the first entry here, 128.178.29/24, that means the first 24 bits, this address. Here, this string has exactly 24 bits, so the first 24 would be, is obvious what it means, but sometimes we give a prefix that is not exactly the number of bits written on the left. So everything that goes to this prefix should go to this next hop. What is this next hop? 100.2. So 100 is this subnet here, and the 100.2 is 100 is probably this one here. So it is this this box here. This is the IP address of this box here. So it is saying anything that goes to this subnet prefix goes to this one. So what is this one? Well, it is a part of EPFL that is directly connected to the backbone. And the part of the EPFL that goes here is the 128.178.29. So it's the 29 subnet of EPFL. And we have one line for this subnet. In fact, we have one line for each of the subnets that are directly attached to this backbone. On this hypothetical example, there's only one end user subnet that's directly attached to the backbone, so we need one entry. Then there is another entry here, which is 128.178/16, and it says you go to .3, which is this router here, and via the interface, which is south. It's the Ethernet, the ETH, the interface. So this box has two communication interfaces, and here it's saying we go to the south one. What does this entry mean? Well, by the virtue of longest prefix match, it means that anything that is an EPFL address and is not this one should go this way here. So it means this is in fact a backbone router that goes to the rest of EPFL, with one exception, which is this subnet is connected directly to the backbone. And another entry, 0/0. Now that's an extreme case. 0 bits means, well, it's the empty prefix. One convention, not always, but often used in the internet, is when you don't know absence of address, you mark 0. If you don't know which address, you need to write an address and you don't know which value it has, you put 0. 0/0 means here absence of address. And which IP addresses will it match? Oh, any. So if this router receives an IP packet to forward, it analyzes the IP destination address. Any IP destination address will match this table. Any EPFL address will match this one, and any address of this local area network will match this line here. So that means here, anything that does not by longest prefix match, anything that does not match those two lines should follow this instruction. And the instruction is saying, go to the north to this IP address, which is the next hop is this machine here. So we can analyze then what happens when we have this table. Well, this table is simply saying, by default, you send everything out to the north here, except if it is an EPFL destination, you send it here, except if it is a very specific destination, which is this one here. So this is how longest prefix match is able to give very compressed address routing tables. Why do we need to have compressed routing table? Well, because every packet that is processed by the router needs to be matched against the entries into the routing table. So we need to do that for every packet. Right? So this is a real-time function that needs to be done going through the table. Enterprise routers tend to have small routing tables so that they don't need exotic technology to be able to read a table in a short amount of time. Backbone internet router, if you're AT&T or other backbone internet routers, you have all the routing prefixes in the world, which constitutes perhaps a few hundreds of thousands, and you need to match to look up those tables in such a fast time. There are technologies for that and dedicated hardware that do it. So that's the principle with, I would say, standard addresses here. Now we will be very often confronted, in fact, with non-standard addresses that I call the special addresses, which in fact in the world of IPv4 are the most common ones. I mentioned 0 everywhere, which means no address here. There's a block of 24 bits, which in practice is often used by only one address. This one, 127.0.0.1, means this host. So this host means if the operating system has a packet to send to that destination address, it will not go to the internet, to the Ethernet or Wi-Fi network card. It will stay into the system. And that's a way that is used for two kinds of things. First, for debugging. If you're deploying a distributed application and you first want to deploy it on the same machine for test, then you simply give this address as destination, and when everything works well, you simply change the destination address in order to reach another instance of your distributed system. And this can also be used for inter-process communication. We will see that TCP-IP sockets can be used for communicating between processes on remote machines, but they can be used for communicating on the same machine. So that's also a form of distributed system primitive called inter-process communication. If you have two processes that communicate together, they can communicate via TCP/IP, even if everything is on the same machine using these addresses. Then we have those blocks that are called private networks. Private networks, for example, if you connect to the EPFL VPN, you will get one of these addresses, the 10 dot something. Those are addresses that are not visible, should not be visible on the public internet. If a Swisscom router sees a packet to destination 10 dot something, the Swisscom routers will say sorry and destination unreachable and will drop it. Those are private addresses, which means two things. First, what I said, they're not supposed to be visible on the public internet. But the counterpart is everybody can use them. So if you build your own private network, you can use those blocks of addresses freely, and someone else will do the same. So of course, if you interconnect your two private networks with these addresses, you will have problems because the same addresses have been used separately. And one of the first principles of IP is every IP interface should have its own unique IP address. So there are 4 blocks, a small block of 16-bit prefix, a mid-sized block of 12-bit prefix, and a large block of 8-bit prefix. They are widely used. At home on my ADSL modem, I have addresses in this block here. So home networks very often use this block, and larger private networks use this or that block here. There is another block which is also private, but is less publicly available, which is used by network operators. For example, Swisscom can use internally those private addresses. They are private in the sense that Sunrise and Swisscom can use the same addresses and it will not be consistent. But however, in the domain of Swisscom, those addresses should be unique here. So they are used by carriers. And the motivation for that is to have addresses that are hidden in some sense to the rest of the world. We will see mechanism for hiding addresses in a few more minutes. So those are specific addresses. Then there are special addresses that we'll talk about later that are used for interconnecting between IPv6 and IPv4. And then there are addresses here that are called link local. What does link local mean? I just mentioned it a few minutes ago. It means same subnet or same local area network. That's a bit strange terminology. But remember, IP views the world as an interconnection of local area network. And all the things that are on the same local area network, we say they're on the same link. A link is another word for a local area network. So a link local address means an address that can be used only between systems on the same local area network. This is typically used, for example, by Windows, when you boot a Windows machine, and it does not have any automatic configuration router to speak to. We'll mention DHCP in a few more slides. So if you connect a machine, it should get its IP prefix and its IP address for someone. You can do it manually, but there are automatic means, but you need a server that will, the machine when it boots will ask a question, who is a DHCP server, give me an address. If this doesn't work, what do? You cannot communicate using TCP-IP. This is what was done 20 years ago with Netware, AppleTalk, etc. Netware, Novel Netware, AppleTalk, etc. Now today we always use TCP-IP. And what you do in such a case is you pick randomly one of these addresses and you test whether it was not already taken. And you have a link local address. Of course, this is very degraded. You will not be able to do much. But if you're standing out in the Pampa and you have a printer and a computer and you want to connect to the printer or the printer of another member of your expedition, that will work. You will be able to connect to those addresses. Question?
Regarding the example with what if you send a message to the local host? So your internet configurator receives something and you send it back.
So the question is, what happens if you send a message to this address? Will the Ethernet concentrator see it? The answer is no. In principle, there's no bug in your operating system. The answer is no, because the semantic of this address is this host. So the host should find a way to deliver the IP packet without going to the network. So this will not go to your Ethernet concentrator. If you want to go to the Ethernet concentrator, you need to use an address that is valid other than this one. We will talk a bit later about multicast, which is a completely different set of things. And there is another special address here. You recognize here all bits equal to 1. And that is the infamous broadcast. That means if I send a packet to this address, I mean to send it to everyone. Of course, if you send to everyone, and if you can send a packet to everyone in the internet, that would be the dream for denial of service attacks. I send to this address and I flood the internet. That would be very easy. So the broadcasts are typically removed by routers, or router will never forward a packet to this address. That's why it is called link local. It means it stays in the same local area network. Broadcasts are a bad idea. They have a lot of security problems, but in local area networks, they are used. Voila, I think it's a good time to do a break. So we break now, and we've discussed about the IP layer. Well, that exists physically in packets that we see in Wireshark or in T-Shark. And this is the format of an IPv4 packet. It has 20 bytes of header, which means overhead. Before I send any useful data, I need first to send those 20 bytes of IP header. The IP header contains the destination address, that's the thing we've spoken more about. Also the source address. We saw last week that this is useful. For example, when a client speaks to a server, the client knows the IP address of the server by going to DNS or finding it through the web. But the server knows the IP address of the client by looking at the source address here. Then there are other things that are, one of them is the total length that we will discuss a bit later. And an important field for us is the protocol. It's called protocol in the IP header, which is a bit strange terminology, but that's rooted in history. It means the nature of the payload, whatever is contained in the IP packet, which in principle is a UDP packet or a TCP packet, because we've seen that the major two transport layer flavors are UDP and TCP. So the protocol is typically TCP or IP, but it can be other things, and it can be a number of other things, but those are the most common ones. One thing that we often find is ICMP. ICMP is an IP packet that is containing information for the management of the IP layer itself. So it contains things like error messages. For example, when we use traceroute, we go to a router somewhere in the world, and then on the path, there will be errors in the routers that would cause ICMP messages to be sent. And if those ICMP messages are not dropped by routers, we will see them. So that's the protocol type. So let's move to a small question. Sometimes we will see things like this mask here. What does the mask, such as this one, mean? I close the poll in a few seconds. Closing. And the majority says D, which is the correct answer. It's a small exercise of decimal to binary conversion. This is what 254 is. 255 is all bits equal to 1. 254 is this minus 1. That means the last bit, you do this minus 1, that gives a 0. Now that means there are 23 bits. So that's a very clumsy way of saying 23. That's the way it is done in configuration files that we can see. Now another question. Here is a configuration. I have a router, an Ethernet switch, a host. Here are some of the configuration information of the router, mask and IP addresses. Which of those IP addresses, A and B, are valid addresses for this host, given what we see in this figure? I'm observing the results, and as they are not correct, I continue to let the poll open. So if you have second thoughts. Okay, closing. And the majority says A, which is not the correct answer in the sense that A is a valid address, but B also. So what is happening here? Well, the first thing to observe is that the host H is in fact on the same local area network as the north interface of the router. That's the key thing. So the principle of IP says it should have the same mask and the same prefix. So it should have an address that starts with the same 23 bits as this. 2.4.8.2 is therefore a valid address. But if we look in details, 2.4.9 has also the same 23 leading bits, which we can verify here. If I write 2.4.9 or 2.4.8, then the first leading bits are the same. So the first 23 bits of this prefix are the same 23 bits of that prefix here. That's one of the tricks of this dotted decimal notation, which is making the happiness of hackers to forge things. And of course, you will need to be familiar with that, although we try to avoid as much as possible in the labs those kinds of weird prefixes, but they exist. Remember, for example, that ETH has a subnet mask of 26 bits and not 24. So those kind of weirdness happen. That was about IPv4, at least the addresses. Now about IPv6 here. IPv6 is the current version, which was motivated, as I mentioned, by the address space of IPv4 being too small. When IPv4 was invented, the computers were huge, monstrous machines, and the inventors of IPv4 did not imagine that we would have smartphones, for example, that require a lot of IP addresses here. So IPv6 was done as a solution to that. And the bad news, or the good news for network engineers, because it gives a lot of interesting inter-networking problems, lots of job opportunities, is that they are incompatible in the sense that if I have an IPv4 only device, which is rare, because if you update your operating system, you will automatically have IPv6. But there are still things that might be IPv4. For example, an emergency button or a telephone in an elevator, or things that are done in hardware, for example, might be IPv4 only. And in some parts of the world, we have IPv4 only services. For example, not far from here, if you go to EPFL via the VPN, you receive only IPv4 service. And last year, with Wi-Fi, you had only IPv4 service. This year, we get IPv6. Perhaps in the coming years, we will get it also over the VPN. In other parts of the world, you might have IPv6 only, not because of software supports only IPv4 only. All operating system software, iOS, Windows, Linux, etc., they all support both 4 and 6, but the network interface card and the network infrastructure might support IPv6 only. That happens, for example, in some parts of the world in cellular networks. Then, in order to speak to B, you must speak IPv6. In order to speak to A, you must speak IPv4. So your software today, if you're at EPFL, has both IPv6 and IPv4. You'll be able to speak to both. Hopefully, the routers at EPFL do both. So we see that, in fact, when we have IPv6 and IPv4, the decision that is to make them as two independent protocols means that we have de facto multi-protocol environment. In particular, we have multi-protocol routers. So a router, when it receives a packet, it has to decide whether it's an IPv4 or an IPv6 packet. If it's an IPv4 packet, it will look up its IPv4 routing table, will do longest prefix match on the IPv4 routing table. If it's an IPv6 packet, it will do the same, but using a different entity, which is the IPv6 routing table. So they are, in principle, separated here. Now, this poses a number of problems. For example, if you have an IPv6 Android or iOS cellular phone that wants to talk to this, then we have a problem. And the problem will require to go via some intermediate system that will do the conversion. We'll talk about it a bit later. Apart from that, IPv6 is like IPv4. I say apart from that, but it makes a huge difference to have 128-bit addresses because it makes everything ugly and very long. Here is, for example, the same diagram as before with IPv6 addresses that are added to the devices of EPFL. You see, that's an IPv6 address. That's how it looks like here. And the routing tables are similar. Here we found the routing table that has, of this backbone router, has an entry for this specific local area network here, which is the 1A4/64 bits. And the rest of EPFL, which is this prefix here, /48, goes via the south interface, which is interface number 2 here. And the rest, 0/0, goes to the backbone, the north interface here. So the notation is a bit different. We'll go through it now. In particular here, we will see that every system has 2 IPv6 addresses. So that's the first ugly part of IPv6, ugly or beautiful, depending on your point of view. With IPv6, every interface that has a global, this is a global IP address, also has a local, link local IP address, has both. When we discussed link local IP address with IPv4, there were many questions during the break about this. The link local IP addresses are meant as a, normally you don't get one of those addresses. When I boot my system at EPFL, I get an EPFL IPv4 address. I will get a link local address only if I'm really stuck in a part of the world where I'm alone with perhaps a printer and 1 or 2 devices. So it's a last resort address that we use, and we use one or the other. In IPv6, we always have both. For what reason? Not clear why. My interpretation of why is that with IPv6, we are ready to get rid of the MAC layer. With IPv6, we're able to communicate with only IP addresses, whereas, as we will see in today's state of affairs, 2 devices, when they communicate, they need IP addresses, but they also need MAC addresses. We need both. And with IPv6, everything is made to be completely, to get completely rid of MAC addresses, which has not happened. The MAC addresses still continue, but the potential now exists. So perhaps one day it will come, but we see it takes 30 years to go from IPv4 to IPv6. So getting rid of MAC addresses perhaps is another 30 years. In IPv6, we also typically see in the routing table interface numbers. That's a consequence of this, perhaps stupid, perhaps smart, I don't know, decision to use link local addresses. In IPv6, every interface must have a link local address. We will see a bit more about that in a few more minutes. And another thing is, if you communicate to somebody and you're in the same local network as that somebody, you use their link local address. You have multiple addresses. If I send a packet to you and we're in the same local area network, I can use your global address or your link local address. Both should work. But the default, the decision is always use the simplest. So if you can use the link local, use the link local, which is why in the routing table, we always see, so what is this? This is the IP address of the next hop of this machine. This is the address of this, right? This is the IP address of this. So in IPv4, we said, in order to send a packet to anybody that's here, you send it to the system that has this IP address. And here in IPv6, the IP address is a link local address. So of course, we need to differentiate different link locals. So we need to physically also instruct the interface number, which was not necessary with IPv4 if everything was well configured with correct masks and prefixes. As you have noticed, we use hexadecimal digits with the IPv6. So they are still, of course, using hexadecimal digit divides by 4 the number of symbols, which is still very long. And IPv6 address exists in 2 flavors, public or private. But the difference, very much like IPv4, with one big difference, is that the private are supposed to not be used if they don't belong to you. IPv4 addresses, I can use the 10 dot something address at EPFL, and ETH can also use the 10 dot something addresses, and we don't need to coordinate the allocation of addresses between those 2, because when used at EPFL, they're truly local and private for EPFL. Private addresses are similar, but still, if you use private address, you need to go through a mechanism of allocation of a prefix, which is this blue and red part here, that in principle is allocated to EPFL. In fact, EPFL has 5 or 6 different blocks, because whoever uses these private addresses should first ask for a prefix. So when we did the smart grid project of EPFL, we said we will do everything in IPv6. After 2 years, we went back and got back to IPv4, but we first started optimistically and say we will do everything with IPv6. So we asked for a prefix, and this is this one, which we get, which is the IPv6 prefix given to IPFL for the people who worked in the smart grid project. Independent of us, other people asked for another EPFL private prefix, and they obtained also one, so that today there are several private blocks here. So this is an example of what you can do when you have so many addresses that you can abuse. When you have lots of money, for example, you become crazy and do stupid things because you're not limited by resources. It's a bit the same thing that's happening with IPv6. Since we have such a large address space, we can do that kind of things, which is complexifying in some sense the allocation of addresses here. Now, because IPv6 addresses are very large, very often we try to find tricks to make them small. And this is useful because there is a rule of how to compress addresses. So those two rules are here. First, we write the IPv6 addresses by what is called a hextet or a piece, which is 16 bits and corresponds to 4 hexadecimal digits, which is here what is given here, 2002, which we can read as 2002. But if we are strict, is not the number 2002 because it's the hexadecimal string 2002, which is much larger than 2002 because this is powers of 16 and not power of 10 that we should do. So if we have this address, we can compress it by doing two things. First, the leading zeros in an hextet can be removed. For example, here I have 0620. I can remove the leading 0. So the understanding is if I have only 3 digits in a block, we should pad it by as many zeros as necessary. That's the first rule. And the second rule is that a block of zeros only can be compressed by putting nothing here. So this double column replaces any number of zeros in more than one piece. So it must be an integer number of pieces. And of course, this should appear only once in any address. If it appears twice, there would be an ambiguity of how many zeros are in each of the blocks. For example, this address here, which has this 1, 2, 3, 4 hextets of zeros, can be compressed here in this. So this is a rule that will be very often used to make addresses look smaller. The current allocated so-called global unicast addresses are the block 200/3. So 3 means 3 bits, not hexadecimal digit, 3 bits. That means anything that starts with the same 3 bits as this string. So the same 3 bits, the first hexadecimal digit is 2, which has 4 bits. And if I expand it into binary digits, I found that the same 3 bits correspond to 2 or 3. So the 2 anything or 3 anything are the valid IPv6 global addresses. What we mean by global unicast address, that means an IP address that is valid in the global internet, which is not private, and is unicast because we will discuss a bit later, also multicast. For example, here is the block allocated to switch, it's a /32. This is the block allocated to EPFL, it's a /48. The block allocated to ETHZ, to Swisscom, etc. There is also a block that is allocated to no provider that you can obtain in order to have an address that is not dependent on a provider. And there are special blocks that we might use for interworking at IPv4. We'll discuss that a bit later. The important thing to remember here is if you compare the blocks that were allocated in IPv4 to switch EPFL and ETH, we see that the block allocated to EPFL and ETH and here are subsets of this block here, right? And even more, we can aggregate. So if a router in California has an IPv6 packet with destination address EPFL, it doesn't need to have a routing table to EPFL. It doesn't need to have this entry in its routing table. It needs to have only switch, because switch is the EPFL provider, and all packets that come from California to EPFL must first go via switch. So the fact that this is now a super prefix of this, which means the net of EPFL is a subset of the set of all IP addresses allocated to switch, makes it compressible. So we can aggregate in routing tables all the different parts that are that are served by the same provider. In fact, that's one of the main benefits of IPv6 for providers. The number of routing table entries that we have for IPv4 is 600,000 or 700,000, whereas for IPv6 it's less than 100,000, if I'm right. So this has led to considerable compression in the routing table, which is one of the motivations for moving to IPv6. As with IPv4, there are special addresses. The empty string, so zeros everywhere. Now we understand this double column means only zeros. It's absence of address. The 127.0.01, the loopback address, is now simply the 1. So this block means as many zeros as you need, followed by a block of 4 digits, which is 0001. That means an address where all bits are 0, except the last bit is 1. That means this host. So for the same reason as for IPv4, it can be used for loopback. Then there are so-called unique local addresses that are the private addresses corresponding to the 10 dot something that I've shown before, and that start with this prefix here, FC/7, which means FC or FD. So anything that starts with FC or FD means a private address. Other than that, you can have an arbitrarily large network. For example, if you're a large corporation or an internet service provider, you might have a network with hundreds of thousands of such addresses and hundreds of routers and subnets and etc. But they are private and cannot be used on the public internet. We have also the link local addresses, which start with this prefix, FE80. It is the first 10 bits of this. And like in IPv4, that can be used only for communication between two systems that are on the same LAN. But unlike IPv4, as I mentioned already, they are systematically used. There is also multicast, and a special form of multicast that we will see a bit later is a so-called solicited node multicast that is always used with IPv6. Whenever an IPv6 machine boots, it uses this address, and we'll talk about it next week also. And there are similar broadcast addresses. For example, if you want to send a packet to everyone on the local area network, you can use this address. But you also have other things. For example, you have all link local routers. That means here, when I'm using this destination address, I'm sending to everyone that one is in the same local area network as me. So I'm sure it will not be forwarded by routers. And second, it will be received, read by somebody who is a router or pretends to be a router. So this is, as you can imagine, used for discovering, for example, when a machine boots, he wants to know what is the routers that are available in my local area. Then you can use this address to contact such systems here. The IPv6 packet is similar to the IPv4 packet with a big exception. Now the address, source and destination address, are multiplied by 4 in number of bits, which makes a header of 40 bytes. Now you can say, well, it's smart because the header was 20. We multiplied by 4 the address space, and we don't multiply the header by 20, by 4, which is true, but it's still large. So that's one of the drawbacks of IPv6. As I discussed last week, perhaps, to some of you, I think this drawback is mitigated. First, on most networks, it doesn't matter because the networks are very high speed and tend to have larger and larger packets. It does matter on low speed networks for Internet of Things that you bitrate and small packets. In that case, you need techniques to compress this. That's another story. Compression, as you can imagine, if you're a local area network router, a local Internet of Things router that is talking to, for example, 500 thermostats in EPFL, the 500 thermostats have an IPv6 address if they use IPv6, but you can map all those 500 addresses to a table which has only 500 entries, and then you can replace this IPv6 header by a shorter header that would have this homemade address, if you want. But there is a standard for that, which is IPv6 for the Internet of Things. But apart from this, the addresses are used unchanged. The second difference with IPv4 is what was called the protocol is now called the next header. So we see that one difference between IPv4 and IPv6 is that IPv6 has a bit cleaned the terminology. The protocol type in IPv4 was a bit awkward. And now it simply means it's the next thing that comes, which is typically TCP or UDP. But as we will see, it can be other things. I will skip this because I need to move to that. But the polls that I skip, I'll post the solution a bit in a few minutes. So we have done a first pass on the IP layer. We're not finished. We'll talk about it more next week. But everything I've presented to you here does not correspond probably to the reality of what you see at home when you connect via your Sunrise or Swisscom or Salt network via your ADSL modem or use your cell phone as a modem here. Because in such a case, you will use a NAT. So a NAT is something that does not behave in the way I've explained the things here. And the motivation was exactly the exhaustion of IPv4 addresses. When IPv4 became a service, which is in the 90s, telecom companies, which used to do things like telephone, SMS, etc., all of a sudden they had to do IP stuff. So the way they did IP stuff was to give you an IP address and a box. So for example, here is the box I received from my telecom provider, and I have only one IP address. And very quickly, and at the beginning, perhaps that is all you needed because you had one PC that was already in the 90s, you belong to the happy few. But today we have lots of devices. We probably have a computer, a tablet, a smartphone, and printers and things like that. And there might be several people in the house that have also devices. So the problem that was solved by the NAT, or Network Address Translation Box, is exactly that one. You receive one IP address from your provider, and you want to have multiple devices, and you don't want to do this weird thing that would be communication at the MAC layer using only MAC addresses. You want to communicate with TCP-IP software as if you had one IP address per device here. So what will you do? Well, you will give a local address here, private addresses. You recognize one of the private blocks here. This is the 16-bit header block, the 16-bit prefix block here. You give private addresses to your devices, and you can give as many as you want. If you have a 10 block, you can give tens of thousands of addresses here. And you can arrange your local area network. That can be here a small network or even a large network. But of course, you'll have a problem here, that this private address here is not visible outside. So I need to map this address here. So this is what the NAT will do. The NAT will transform the source IP address to the IP address that it has received, which is the only legal one it can use to reach the rest of the world. This is what the NAT will do. So during many years, this has been a way to solve the problem of not having enough IPv4 addresses, because as we see here, we use only one for N devices here. And this is also now largely used for virtualization. In VirtualBox, we use exactly the same thing. In VirtualBox, we have our computer, and our computer receives an IP address. And this IP address is, for example, given to us, that's by the Wi-Fi of EPFL. Then inside my computer, I create a virtual network that will use other IP addresses and wants to be able to communicate with the rest of the world. So we will also use a NAT in the lab. We will use 10.something addresses here. And the NAT will make sure that those addresses are translated to this address here. So the NAT is our first example. It's called the middle box. So the middle box routers are middle boxes. Ethernet switches are middle boxes. So that's another word for intermediate system. But it's a middle box that completely violates all the principles of TCP-IP. It deviates from the TCP-IP principles. It violates two things. It violates the first principle that we should have one IP address here for everyone. And an intermediate system should simply forward the system, forward without modifying the destination address. nor the source address, by the way, which is what it is not doing. It violates another principle, which is layering, because for its operation, the NAT will look not only at IP addresses, but also at TCP or UDP port numbers. So it looks at 2 layers at a time to do its job. That's ugly. If you would build an architecture today, you would not do that. So it was not at all part of the internet architecture, but it came as a practical solution to a practical problem. This is where the internet is the result of architecture, but also evolution. And it has become so dominant that today there are also RFCs, so it is retrofitted into the architecture, but as an afterthought. So it's important to remember that it deviates. Otherwise, it's impossible to understand what a NAT does versus what a router does. So the NAT has to translate the internal addresses. So I call internal addresses the addresses that are in my local area network at home or in my virtual network or virtual box in the lab here. It must translate them into an IP address here. So whenever a packet, for example, here I'm showing, what am I showing? I'm showing a packet that goes from S here, a server that's on the internet, and goes to A here. When S sends a packet to A, the only destination address it can use is the destination address of the NAT, which we see here. And similar when it sends a packet to B. So of course, NAT will translate the address, but we still have a problem. How does the local area network and the NAT know that the destination is A or B? So we have multiple addresses that we need to put into one. Of course, that doesn't work. The pigeonhole principle. If you have one address, you cannot merge 2 with the same number of bits. So we need more bits to multiplex these addresses. And the smart thing of the NAT is to use those bits from the port numbers. So when A speaks to this guy here, for example, using UDP, it uses perhaps a local port. We've seen that with UDP, you speak to a server using the well-defined, well-known server port number. But the source, the client port number, is a random number given to you by the operating system. So assume those 2 started at the same time, have the same device, do the same thing. So perhaps they get exactly the same local port number, 1029. That's the port number they have received for communicating to this S over UDP. That's using Skype, for example. Now, what will happen is that the NAT will have a table where it will, if there is a collision in port numbers, because it uses the port number to differentiate the hosts here, it will modify the port numbers. So when a packet, for example, goes from A to S with this source address and source port number, the NAT sees, oh, now I have a packet that goes to the outside. I need to remember this combination. So the NAT will have a table, has a table, with the list of all the conversations it has seen. Of course, this is not scalable. It works for you at home when you have a few devices and a few flows. It has a table that can be a few thousand lines. It would not be scalable if you would use that in the global internet. So when it sees a packet here, it puts this entry in the table, and then it will choose a port number, one that has not been used. If it sees another packet from another source, so if it's from the same source, then there's nothing to do. If it comes from another source address, which is here B, it needs to change the port number. So it will modify the port number in the packet that is sent on the internet, and it will remember the change that it does here. So the NAT will forward packet now based on this table. When a packet comes from the outside from S, it is to the NAT. Now the NAT knows that when it receives a packet to itself, it needs to look at the port number, because the NAT may also have a web server running into it. This is, for example, how the operator might log into your modem to do something. So if the port number is one of the internal management port numbers, then it knows that's for me. Otherwise, if it's a port number that is in the table, in the NAT forwarding table, it means, no, it's not for me. I should act like a router, but a cheating router, a router that cheats because it does those weird things. So it looks in the table, it says destination IP address is that I've received this one. I go to my table, I map this combination of IP address, which is me, and this port number into this IP address and that port number. And I modify in the TCP header the port number, and then I send it to this IP address here. This is how the NAT will be able to have communication between S and A and between S and B. For S, for the rest of the world, everything is happening as if everything was in the NAT. You have, in fact, a computer here with two processes that are speaking to the same server. If we had a computer that's natively connected to the internet with two processes, one that uses this port number and one that uses that port number, then that would be exactly the same seen from the outside. So from the outside, when we have a NAT, we are unable to see how many machines are actually talking to us. We cannot make the difference between multiple processes in one machine or multiple different machines. In particular, those IP addresses are invisible to us. Of course, they must be invisible because those are private addresses. The main difference between a router is now that the matching that must be done in the table is an exact match. I don't do longest prefix match. I must find exactly a port number that corresponds to this, and in the reverse direction, similarly. So we've seen communication from the outside to the inside. We see here communication in the reverse direction. So it's exactly the converse here. In packets from internal to external, the NAT translates the source address and the port number, and the internal addresses are typically private addresses, typically always private addresses. Now, because of course, how does the NAT maintain this table here? How does it do it here? Well, the answer is it does it on the fly, automatically. That's the default answer. You can, if you work a bit on the documentation of your modem at home, you can find how to log into your modem, and you can write such association entries in your table. So you can do it by managing your modem, your ADSL box here, which is often called your modem. But it's not very smart. That was the thing that we would do 30 years ago. Right? At the very beginning of internet, you had to know how to manage things in the NAT table in your system for some applications to work. But today, it's not always done, or quasi always done on the fly. And on the fly means whenever A connects to a server, imagine this is a web server, then communication is initiated by the client. So the client will first grab a port number that is given by the operating system to A, and the first packet of this conversation is originated from the client. Then when a NAT sees a packet, it will always ask itself the question, is this a combination of source IP address, source port number, destination IP address, destination port number? Is it already in my table? If it is, then nothing to do. If it is not, I create a new table entry and I choose a new port number that I put in the table here. Of course, one that does not create collision. And this is possible because the number of port numbers is typically much, much larger than any single system uses. If I had a single system here that would use all the possible port numbers that can exist here, then this would not work. But this is not the case here. Of course, I mentioned that this automatic association is done because typically it's a client that's sitting behind the NAT and connects a server, which is a typical case. Most of us don't have servers at home, but some do. For example, for home automation, you might have a device that you want to connect from your home. So what happens if you have a server on a TCP port at home? First, if you do this, you should make sure you have a server that is well patched, because it will be receiving a lot of attacks from the internet. But the system will not work. Right? Because when a client will connect to my server, this association is not done on the fly because this port number 5000 is not known by the NAT, so it works only in the reverse direction. So you need to do it by, as I mentioned, going manually. The terminology that's often used in the docs is port forwarding. It's called port forwarding. So you need to manually write a table entry that says, for example, any packet that comes to this address. So if your server is on this address, the one you will make available to the rest of the world is not the address of your server, but the address of your box here, which hopefully doesn't change too often, or if it changes too often, you need to put it in a dynamic address with dynamic DNS. So you put this address you inform C of this address, of the port number here, that is 5000, and then it will need to be translated to the port number that's understood by here, which in most cases will be the same here. And since you do it manually, it's your job to not create collisions. You have two devices that have the same port number here. You will need to export to the rest of the world a different one here. So this is the drawback. But in the recent time, it has also become an advantage because since in order to have a server at home, I need to first configure something, which means I will not inadvertently have a server running at home. That's good news. You might have a server port that's open on your computer or your device. It will not be reachable if you don't actively do something. So it provides protection to the home network. And second, it provides also, the protection is also in the form of filtering. Here, I'm allowing only traffic that goes explicitly to this port number. Here, every traffic that goes to another port number in my local area network will be discarded by the NAT. The NAT that I've shown are for IPv4. And in fact, the motivation for NAT is IPv4. To the extent that we find very little NAT functions or software for IPv6. And in fact, as we will see, we use it in the lab with IPv6, but sometimes it doesn't support everything the way it should. Why is that? Why was NAT developed for IPv4? Well, because the motivation was the lack of IPv4 addresses here. And because a NAT is a violation of the principle of IP, the people at the ATF, they did not like it. They never liked it. So for IPv6, they said there's no need for NATs for IPv6 because the shortage of address does not exist. So there's no need for IPv6 NATs. So for many, many years, there was no IPv6 NATs available, apart from a few prototype implementation done in a few corners. Now there are some, but still it is, as we will see, not widespread here. For example, most home devices, your box here, which you can call your home router, will probably not do NAT for IPv6. Instead, because now the IP addresses are so large, it will receive for the provider not one IP address, but a block of addresses. Since there are so many bits now in so much space in IPv6, typically your home router will receive a block, and then you can allocate addresses from your block to your home systems here. Which means that the IP addresses that you have for IPv6 at home are global, valid addresses that don't need to be translated, unlike for IPv4, which is good. If you want to ping and things like this, it makes things simpler, but it's also bad because that means now your IP addresses are visible to the entire world. So that provides less of a protection here. So typically home routers, when you do this, they will act as filtering routers. Now, your home router for IPv6 is not a NAT. It's a regular router. It receives a prefix from your internet service provider, and your home network uses this prefix. So it's a regular router, uses longest prefix match and all the like. But it will do what we call filtering. For example, it will look at all packets that are SYN packets, so there are packets that go to a TCP server, and it will kill them, because you're not expect to have a TCP server at home, except if you manually configured it into your IPv6 home router. However, so that's for home. For home, IPv6 will not using a NAT. But in the virtual box, we still need that because EPFL doesn't give us a prefix when we connect to Wi-Fi IPv6. We're already very happy. Thank you, EPFL, for giving us one IPv6 address over Wi-Fi. Now for VirtualBox, Perhaps we can post a ticket to say we would like to have a prefix, not an address, but this is not usual because you're not supposed to be doing a network when you're moving around with your mobile device on a Wi-Fi network. So you receive just one IPv6 address. So in VirtualBox, we still need a NAT. Right? So for a NAT, then we will need private addresses. Private addresses, depending on the version of VirtualBox that you use, can be either link local address, if you use one of the several NAT configurations of VirtualBox, that provides you only a link local area network in the virtual environment. If you want a more sophisticated network, you can use private addresses that are given by Oracle, so the provider of VirtualBox software. So they give us private addresses, very much like we did with IPv4. So this is what we will be using in the lab here. We will have a NAT with IPv6. Sometimes you even use NATs at larger scale. They are called carrier-grade NATs. And perhaps since we will not be using them in the lab, I think it's time for me to stop here, since we're timing out. So thank you very much for your attention today, and enjoy the lab and the quiz.